In this video, I'm going to focus on rotational inertia. Let's start with inertia. This is how much an object resists changes in motion. On the left, we're looking at two blocks. Each are at rest on the ground. The goal is to lift them upwards and change them from resting to moving. On the right, we're looking at two spheres flying through the air. The goal is to stop them or catch them and change them from moving to resting. So in each case, which one would be harder to change the motion of? We would want to choose the 10 kilogram mass, the heavier object. It is always harder to change the motion of the heavier object, so an object's inertia is directly related to its mass. As we transition into rotational inertia, let's start with an example. Let's say you're holding two hammers, one in each hand. In your left hand, you're holding the hammer by its handle, and in your right hand, you flipped it around. You're holding the hammer from its head. Let's say that you rotate it up and down a few times. And the question is, which hammer would be harder to rotate? If you tried this out, you would find that the hammer on the left, the one held from the handle, is much harder to rotate. It's much harder to change the rotational motion of. So therefore, we would say it has more rotational inertia. But why is that? It's the same hammer, it's the same overall mass, and as discussed on the last slide, it has the same overall inertia. So there must be something more to rotational inertia than just the overall mass of the object. Let's first define rotational inertia. It is how much an object resists changes in rotational motion. The variable is capital I, and it's measured in kilograms times meters squared. The equation is that it's equal to m times r squared. M is the mass of the object in kilograms, and r is a distance. It's measured from the axis of rotation to where the mass is located, measured in meters. And I'll talk more about this r variable in the slides to come. The first thing you'll want to do when considering rotational inertia is to define your axis of rotation. This is the fixed part of the rotating object, or the part that does not rotate. So for our hammer rotation example, it would be where your hand is located. That is where you fix the object to your hand, and although the rest of the hammer is rotating, the part that's touching your hand technically does not. Know that the axis of rotation is where r is equal to 0 meters, and we make our measurements from that point. As we go back to our hammer example, let's first talk about the hammer. The majority of the mass of the hammer is located at its head, so that's where we're measuring to. On the left, when we rotate from the handle, there's a large distance between axis and mass, whereas on the right, there's a much smaller distance. Being that in our equation, distance is proportional to inertia, the more distance, the more inertia, and this should explain why the hammer on the left is harder to rotate. So when you think of rotational inertia, it's not only the mass of the object, it's also where that mass is located relative to the axis of rotation. When studying rotational inertia, I think it's important to know the difference between a point mass and a mass distribution. Let's say we're looking at this random example of the Earth, and we've got a basketball orbiting it, much like a satellite would, and let's call the distance from the Earth's center to the basketball as the distance r. The question is, where is the mass of the spinning object, or the basketball? Well, in this example, it's all located at the same position. Relative to our axis, the entire basketball is the distance r away. So when the mass is located at a single point, it is described by the standard inertia equation, I equals mr squared, and know that this inertia is independent of the shape of the rotating object. Let's look at a mass distribution. Here we're spinning a basketball on top of a finger. The axis runs where the finger is, and the distance r is measured from the axis to the outer edge of the basketball. Again, the same question. Where is the mass of the spinning object relative to the axis? Well, this one's more complicated. Some of the basketball is on the axis, some is to the left, some is to the right. It's distributed over multiple areas. So when the mass is distributed over different locations relative to the axis, it's known as a mass distribution, and it gets its own rotational inertia equation relative to the shape of the object. On this slide, I'm just showing 6 of the more common mass distributions you might see, and also their respective inertia equations. You might want to pause the video here and add these to your notes. The last thing to discuss would be center of mass. This is a position that represents the average location of a system's mass. This is not necessarily at the geometric center of the object, although it could be. Looking at 2 examples, a meter stick and a hammer, we're going to try to choose which position represents the center of mass of each. For the meter stick, we choose position B because the meter stick has a uniformly distributed mass, whereas the hammer has more mass on its right edge than its left, so we would choose position C. The center of mass is shifted to the right. This is important for rotation because going forward, you always want to draw your force of gravity on an object as acting from its center of mass.